Hello. Now, before you move, there's what we call motor planning. And this involves the communication of different brain regions to make your movements possible. Now, these communications could either be excitatory in nature or could be inhibitory in nature. And that's indicated by the blue and orange, respectively. Now, after this motor planning phase, the brain then sends commands to your muscles for you to make these movements. Now, these movements could either be sent via a specific pathway or a non-specific pathway. Regarding the specific pathway, these actually branch to more specific targeted neurons that connect to your muscles. And these actually project more to distal muscles, such as your fingers. And so it's likely that when you are playing a piano or a guitar, you are likely engaging more of your specific pathways. Now, for the non-specific pathways, these are non-specific, like the name suggests, meaning that they branch to multiple segments, and thus engaging these pathways would likely increase activation of muscles of different parts of your body. Now, these non-specific pathways actually originate from what we call the brainstem, and that's indicated by the red boundary. And these receive projections from higher brain regions. And so it's likely that these higher brain regions can then modulate these non-specific pathways depending on the type of movement you want to make. Now, I'd like to say that although these non-specific pathways branch to multiple segments, they mostly prefer more proximal muscles, such as your shoulder muscles. So it's likely that if you are lifting your arm, you're likely going to be engaging more of your non-specific pathway. Now, because of the difference in anatomy and function of these two pathways, it is likely that depending on the type of movement that you want to make, the brain is going to either use one pathway relatively more than the other pathway. So then I ask this question. How and when does the brain choose to use one pathway over the other? And what happens when one pathway is damaged? And this is particularly the case when you have a stroke. And in stroke survivors, most of the time, they lose the specific pathway, as well as the pathway that regulates the brainstem and the non-specific pathways. And in such cases, what we see is that when you ask these stroke survivors to open their hand, they are relatively able to do so when they are supported by a table. However, when you ask them to lift up and open their hand, now this is where the challenge begins. And what we see is that they flex their fingers and wrist, as well as their elbows inwards. And this affects their hand opening ability. Whereas in able-bodied individuals, we are able to lift up and open our hand successfully. And so this means that in a healthy brain, like an able-bodied individual, it means that there is some kind of modulation within the brain to regulate the use of the non-specific pathway, such that we are able to selectively use different muscles at a time. And so then this begs the question, when and how does the brain selectively engage one pathway over the other when you want to selectively use one pathway and selectively use different muscles? And so to study this, what we do is to startle people. Now, we do this because the startling response has been recognized to be facilitated via the non-specific pathways. Now, I'm sure we all have experienced being startled before. However, if there's someone in this room who has not experienced this startling response, I'll explain what happens, and this is exactly what happens. When you get a loud acoustic stimulation, we flex our entire muscles, and this has been shown to be because the loud sound triggered the activation of what I call the giant, and that's the brainstem, leading to the response being facilitated via the non-specific pathways. But science has shown us that when we are planning for a movement, such as opening our hands, for example, we elicit this movement very rapidly and involuntarily when we get startled. And this has been associated to the same mechanism as the startle response being facilitated via the non-specific pathways. So this gives us a clean way to tackle non-invasively how we use the non-specific pathways and when we use the non-specific pathways. And so therefore, we use the startle to investigate how the brain modulates the brainstem and thus uses one pathway over the other. And how we do this is by recruiting able-bodied individuals into our lab, and then we place them in this configuration and then provide them with a preparatory cue. telling them that once they hear this cue, they start preparing for a movement. However, when they hear a second cue, they should move as fast as possible. And now this cue could either be of a startling intensity or a non-startling intensity. And by so doing, we can quantify their response at different stimulation conditions and in different types of movements. And then if the movement in a particular stimulus condition is reduced, this can help us identify which kind of pathway they are using relatively more than the other. And so then I've told you how we do this. But why do we do this? We do this because it solves mysteries. Now, the brain is a very beautiful yet complicated structure, and we still don't fully understand how it works. My research seeks to just bridge this gap in just understanding just a little bit of this brain's puzzle. And if we are able to solve this mystery in able-bodied individuals, we can then understand how disease, like stroke, affects this communication and how the brain functions. And by so doing, we can then develop ways to combat this disease. So I invite you all to participate in my research and join me in solving this problem quicker. You can reach out to me after this, during the break, and we can discuss further. Thank you very much.